The other thing we'd like to talk about would be the minimum speed. The minimum speed that a roller coaster is capable of, the minimum speed required for a roller coaster to make it through a loop. It's a fairly simple concept, so I'm not going to spend a tremendous amount of time here. All we need to realize is as something goes through a circle, it must be experiencing a centripetal force acting towards the center, as well as a centripetal acceleration acting towards the center as well. The idea here is very basic. The top is the critical point. I think most people realize the top is the point you want to get past. That's the point where you're either going to fall off or you're going to keep on going. And if you think about it, if you fall off, the only thing acting on you is gravity. You're in free fall. You do not want to be in free fall at the top of a roller coaster because that means you're just falling towards the bottom. So, conceptually, if the centripetal force at the top is only gravity, meaning you have no normal force at that point from the track, it's literally just gravity acting on you. Well, if we remember, projectiles, objects in free fall, these only have gravity acting on them. So, what we're saying here is we do not want this to happen because that means the car is in free fall. If the centripetal force is only gravity, or the centripetal acceleration is only little g, 9.81 meters per second squared, you are officially free falling towards the bottom of the track. Not a good situation to be in. So to find the minimum speed, the only thing you need to realize is that FC equals FG or AC equals G. They're both going to be true at the same time, so it doesn't matter which one you use. That car will free fall at the top of the track. That's not a good thing. That's not safe. We'd like to avoid that. To show you a quick example of this, and again, we just want to avoid that free fall condition at the critical point, which is the top. I want to know what minimum speed must this cart enter this loop in order to safely navigate the turn. Well, if I draw a free body diagram at the top, because that's the critical position, if this is not safe, gravity will be the only force acting on it. There's no normal force in a critical case, and that's really what the problem is. You don't have the cart helping to push you through this loop anymore. Gravity has officially taken over. When gravity takes over, you are in free fall. So if gravity is the only force, we'll look at our math here. Centripetal force would only be gravity in that case, which would be a bad thing. I can't stress that enough. So the centripetal force, which is gravity, would be equal to mv squared over r. So if we calculate gravity using Fg as mg, we find that the gravitational force on that cart would be 19,620, and we would just set that equal to our centripetal force calculation. Plug in the known values. We have everything known except for velocity. I'll go through each of the steps here. I won't talk about them, but multiply each side by 20, etc., etc. If you solve this through, you will find that the minimum velocity you must travel at is 14 meters per second. And we found that by quite simply just stating that the centripetal force is only gravity. So what that means is if I enter this loop at 14 meters per second, or higher, I should be fine. It'll be a little bit scary. It'll almost feel like I'm about to fall off, but I should make it. If I enter at less than 14 meters per second, I'm either going to get to the top and fall, or I'm not going to have enough speed to get up and I'm going to fall back down. So, 14 meters per second, how is that found? Well, that was found by realizing at the top point, if FC is only FG, it's not a combination of some forces. If it's only gravity, I'm in free fall at that case. And this is the velocity that will result at. You do not want to. You technically would like to go faster than 14 meters per second in order to safely get through this.